I'm here to introduce our speaker, who's Tim Orr. So Tim Orr has been a member of the NAWCC for more than 30 years, and he's a Silver Star Fellow who's served on the NAWCC board from 2013 to 2021. Currently, he's a member of the Nominating and Elections Committee. Actively, he's seeking candidates for the future board positions. His interests in timekeeping were sparked by a father, who was also a longtime member of the NAWCC and an avid collector of clocks. Tim, as so many of us do, began by collecting shelf clocks. And then when he ran out of shelf space, he switched to wall clocks. When he ran out of wall space, he took some advice from another member and began collecting wristwatches. He has also developed an interest in electromechanical clocks after working as an announcer in a radio station that had a number of synchronized self-winding clock company clocks. Tim's interest in time zones and the longitude problem came about after reading Dave Sabell's book on longitude and other material by Rupert Gold. He likes to go back to first principles in understanding complex things, and even read some children's books on longitude and navigation when he first started looking into the subject. He titles his talk Longitude for Beginners, but hopes it will not be too elementary for listeners. With that, I'll give him the floor.
Well, thank you. I may need a little direction. I'm going to share screen here. And there we go. And all right, I trust everyone is seeing a blank screen, which is exactly what I'm after. So the talk I give is called Longitude for Beginners. One of the things I want to say about that is that the more I find out about longitude, the more I find out about navigation at sea during the 18th century and before. And the more I find out about chronometers and timekeeping and all that sort of thing as an adjunct to the determination of longitude, the more I realize that I know next to nothing about this subject. So knowing that I know next to nothing, let's go forward. The big problem was uncertainty when you were at sea. There were a bunch of things that influenced that, amongst them ignorance, misfortune, and coincidence. And so we'll see a little bit about all those things in this talk. 1739 through 1748 was called the War of Jenkins' Ear. It's a war between Britain and Spain, who had been at war numerous times. And when you hear about this, you realize what silly or small pretexts they would go to justify going to war. Apparently, there was a battle at sea between a British ship and a Spanish ship. And in the course of the battle, the only casualty was a fellow by the name of Robert Jenkins, who lost his ear. And so they said, well, that's good enough. Let's go to war. So they did. So anyway, this was a frequent occurrence during the 18th century. England decided that it should raid Spanish treasure ships in the Pacific Ocean. But how do you get from Britain to the Pacific Ocean? There was no Panama Canal. There was no Suez Canal. So the only way to get to the Pacific from Britain was to do it the same way that Magellan and Drake had done, and that was to go around the southern tip of South America. So they got this man, Commodore George Anson, and sent him out in 1740 with 6 ships. He gets a very, very late start, and it is winter before he reaches the Straits of Magellan. So it's wintertime, and he's all the way down at the southern tip of South America. And the Straits of Magellan, you see the map pin there, the red map pin, that's the Straits area. The entrance, of course, is up to the right, little tiny point there, which is where they're going to enter the straits. As they enter the strait, this is sort of what they see. Now, this is obviously a modern photo. There were no photos from 1740, but this is about what it looked like then. It's pretty much deserted, and it's the point of entry into the strait. The point is called Punta Dungeness, which simply means Dungeness Point, because it resembles Dungeness on the coast of Kent, southeast England, and this is that Dungeness there. So that's how it got its name. Anyway, the idea is to thread your way through the Strait of Magellan from the Atlantic to the Pacific. But there's a problem for Anson, which is that both Chile and Argentina, those areas in 1740 are both Spanish possessions. So he has to try to sneak through the straits and cannot put ashore for either supplies or water because they're at war. So the weather is very, very bad. As I mentioned, they didn't get started until almost the dead of winter. They have, during the time they're going through the straits, they experience snow, hurricane force winds, thunderstorms, rain, ice storms, fog, high seas, strong currents, and so on. It takes them 6 weeks to try to get through the strait. And 2 of the 6 ships that Anson had been given had to give up and return home. 1 ship was completely destroyed. So he's only got 3 left. And finally, the weather clears, and they figure that they're at the end there where the arrowhead is, and that they're probably, you know, easily a few miles past the strait. So they do what sailors in those days did, which is then they say, okay, we now need to head north to get into the heart of the Pacific. And they would do that and start plundering Spanish treasure ships. They turn north, and almost immediately they sight land. And where they're going is they're going to this map point here off to the west. So they head north, and the first thing they see is this. Imagine their horror. They're still on the Atlantic side of the Strait of Magellan, 6 weeks of terrible weather. They're back where they started from. They've been completely turned around, and they're back out on the Atlantic Ocean side. Now things are really, really bad. They've lost 3 ships. They're low on food and water. And now they have to go through the strait yet again. Worst of all, they are suffering an epidemic of scurvy. This is a very, very bad turn for them. So they make the journey through the strait again, and in horrible weather again, but this time they manage to get through and end up getting through to the Pacific Ocean. So we come to uncertainty number one, which is longitude. In those days, there was no way to calculate longitude accurately. The technology simply did not exist. So they would do things like they would estimate the ship's speed by dragging a log, which originally way back perhaps was a log, but it wasn't a log. But in those days, it was a much more sophisticated float. And they would count the number of knots in a rope that went past the navigator's hand while dragging the log. And they used a sand glass to time those knots and calculate their speed. They would estimate direction using a compass. But here's an issue. Compasses vary depending on where you are. So you see the green line there, that's 0. And that says that the compass deviation from true north is 0 there. But as you get down to the Straits of Magellan, you're now at about 12 degrees off. And by the time you get through the Straits of Magellan, you're 16 degrees off. So it's not a really good thing. As a consequence, of course, they lost track of where they were and got lost in the strait. And the only thing that they would know fairly well is their latitude. The latitude was something that they could calculate and that they knew very accurately. So how did they figure out latitude? Well, latitude is pretty easy to measure. You're only trying to determine north and south of the equator. And you use a sextant to measure the altitude of a star. And they either cite the pole star, Polaris, or what we call the North Star. But if you're below the equator, you usually would use Sigma Octantis, which is a star that is near the South Pole. You can see here that the difference between Sigma Octantis and the actual South Pole is pretty small, and you use the Southern Cross and the Southern Pointers to get you into the vicinity of Sigma Octantis, and then you're able to find it. You know, the Australians use the Southern Cross as a very key image in their mythology. So what you then do is, because you can figure out latitude very well, is you try to find the latitude of your target and stay on the same latitude as the target. And then you only have to sail either east or west to get to your destination. So that's what Anson was going to try to do. He was going to get to the latitude of his destination and then sail either east or west to get there. But because he doesn't know his longitude, he doesn't know whether to go east or west. So uncertainty number 2 is one we don't often think about, but here it is: scurvy. It's a very, very rare disease today. But at this point, Anson has lost 626 of his original 961 crew members. That's like 2/3 of his crew is gone, is dead because of scurvy. So he is very concerned that he may not have enough men to actually sail the ships. And nobody knows the cause of scurvy. And he cannot put ashore for food or water, even though it is well known by that time that the quickest way to cure scurvy is get the people to shore, get them fresh food, get them fresh water, and they will recover rapidly. But he can't do it because he's in Spanish territory, and he would be entering a state at which they're at war. So his destination is a small island, actually a small archipelago called Juan Fernandez. And it's about 300 miles west of Chile. and it's about 1,500 miles north of the Straits of Magellan. They have no alliance with Spain. And so as a consequence, they're a totally monetary driven operation. If you've got money, you're welcome there. And they don't care what country you're from. This is where he can get supplies, where he can get food, water, and the opportunity to put his men ashore and get them cured of their scurvy. Juan Fernandez is at about 33 degrees south latitude. And so he says, okay, what we need to do is sail north to 33 degrees south and then decide what to do. So again, the map pin here, the red map pin, is at about 33 degrees south latitude. You know that you can see that Santiago in Chile is approximately at the same latitude. And they know that Juan Fernandez Island is somewhere on a line going horizontally through that map pin. But because they do not know their latitude, or their longitude rather, they're not sure where on that line the island is. So they do what any good sailor in those days would do, and that is they start heading along that line, hoping that what will happen is they'll run into it. So the question is, when you're at 33 degrees, do you turn west or do you turn east? And they don't know because they don't know their longitude. So they guess, Anson guesses that Juan Fernandez is west of where he currently is, and he starts sailing west. So what happens is he sails west for 3 days on longitude 33. And what do they see? Nothing. Nothing at all. There's no land sighted. So their thinking becomes, well, maybe we were west of there, when we started out. And we're just sailing out into the Pacific Ocean where there's nothing at that latitude. And so they say, okay, what we better do is we had better turn back. So they sail for 4 days east, and they sight the coast of Chile. So they know at this point that they had not gone far enough west. And in fact, based on later calculations, if they'd only gone just a few hours more, they would have made landfall at Juan Fernandez. So the trouble is that, a bad situation that they had to begin with is only getting worse. In fact, as they retrace their steps, they lose 70 more crew, bringing the total loss to nearly 700 men lost to scurvy and other problems. But eventually they get there, they reach Juan Fernandez, they resupply, the men recover, and they actually then go on to their mission, which is to plunder Spanish treasure ships in the Pacific. And this is the ship that, model of the ship that they used. This is the HMS Centurion, which was built in 1732, and their voyage was 1740. So the ship was not terribly old at that point. That's the flagship. And the fact of the matter is, they did very well. They captured millions of gold doubloons and other treasure from Spanish ships in the Pacific Ocean. And the voyage, from a financial standpoint, was considered to be a huge success. So we had our first thing, which was uncertainties. How to find longitude and how to cure scurvy. Scurvy, as I said, was a serious disease that killed people. And there was no effective cure or prevention until nearly 1795. That's half a century later than Anson's voyage. Of course, we now know that citrus, fresh fruit, and even sauerkraut, interestingly enough, all proved to be effective treatments for scurvy, but they didn't know that then. And of course, we now know that scurvy is a vitamin C deficiency as a disease. So that was one of the great uncertainties of the 1740s. The other, of course, is longitude. In 1714, Parliament established a longitude prize. It was 20,000 pounds, which is equivalent to roughly $12 million today. And a whole bunch of people, as you can imagine, said, well, I've got to solve that. And so some of the things that they tried were purely astronomical methods, which were both mathematically and astronomically difficult. You know, for example, we know that the moon crosses the sky at night, and if you could measure the position of the moon, theoretically, you say, okay, I know how long it takes to go across, and so I can measure the position of the moon in the sky and thereby determine the amount of time that has passed since moonrise. And if I do a whole bunch of mathematical calculations and so on and so forth, I can figure out what time it is at any given sighting, and compare that with the time that I know from the astronomical tables, and figure things out. Well, there were a number of problems with this. First of all, this was hard to do. This was intensely mathematically difficult, and there were very, very few skilled mathematicians on board ships of the line. It was also astronomically difficult because you can't always see the moon. There are clouds and mist and fog and all kinds of other things that make it difficult to do this. So this proved to be an ineffective solution. And time became a more practical answer. So we asked the question, how do we know the time in two different places on Earth at exactly the same moment? So we'll look at the basics. The Earth rotates once every 24 hours. So that means that it rotates 360 degrees every 24 hours. And if we do the math, simple math, it means that 15 degrees rotation occurs every hour. And doing even more math, 1 degree of rotation takes 4 minutes. So we know that we can use this as a way of figuring out where we are. So we have to decide where we're going to start. And so the British, of course, obviously we're going to choose London as the prime meridian, the first meridian. And so they use the Astronomical Observatory at Greenwich as their prime meridian, or 0 point, reference point, starting point, etc. And we know this: if it is noon where we are and 1 p.m. at Greenwich, then we are 15 degrees west of Greenwich, and we know our longitude. So by convention, we say west of Greenwich is minus and east of Greenwich is plus. So the answer is, if we know the time where we are, and if we know the time at Greenwich, we can figure out the longitude. So how do we find the time where we are? Well, we use a sextant and astronomical tables. The position of the sun and so on at any given time is very well known. We can measure it very, very easily most of the time with a sextant. and make some relatively simple calculations, mostly just addition, subtraction, multiplication, and division. And we can figure out what time it is, where we are. And how do we know the time someplace else? Well, we need some kind of a chronometer. And I say some kind of a chronometer because a lot of different ideas were suggested. One of the most bizarre was a fellow had two dogs that were from the same litter, and he claimed that if he harmed the one dog and he would stick it with a pin or a knife, and he believed that if he stuck the one dog, the other dog would howl. So his concept was, what we're going to do is we're going to put one dog on board the ship, and we're going to keep one dog at Greenwich. And at noon, we're going to stab the dog at Greenwich, and the dog on board ship will howl. And then we'll know it's noon. And he actually tried to sell this to the Longitude Commission. The other was a thing called, the thing of moons of Jupiter. There were a number of moons of Jupiter, and they rotate at different rates. And Galileo had been one of the first to notice this. And they said, well, you know, if we know the different rates that the moons go around, and we can cite those, we can figure out what the time is. Well, again, this was plagued by the same kind of astronomical difficulties. You had to have a really good grasp of mathematics, and you had to have a really clear sky and a good telescope so that you could sight Jupiter and figure out the positions of these moons. Needless to say, it was doomed to failure. Of course, nowadays, or later on in the 20th century, we had the radio chronometer, where we could actually broadcast a time signal that could be picked up on board ship and used to know the time at Greenwich. But of course, this was not available to Anson in his day. So how do we know what time it is at Greenwich? Well, John Harrison, who had been a carpenter, a cabinet maker, and a creator of clocks that were incredibly precise, figured out a way to do this. And he invented a clock that could be carried on board ship and was resistant to temperature changes, was resistant to the motion of the ships, and was resistant to the wear of parts. One of the most astonishing things about Harrison's early chronometers is that the several that he creates, H1, H2, and H3, which you see there, they don't require any lubrication. And you can go to the Greenwich Observatory in London, and you can actually see these machines, and frequently you will see them running 300 years later, and they're still running, and they don't require any lubrication, and they're still able to keep good time. He finally created a much smaller one, like a giant oversized pocket watch, H4, but it does require oil. And H4 ended up being the prototype for what would be taken on board ships. H1 was huge and heavy, and really wasn't practical for use on board a ship, but nevertheless, it did keep good time and was able to help them figure out their longitude. I show this chart. I show this. This is a 19th century chronometer. You can ignore the tables they're at the top and running sideways. Here's what is important: is the notes towards the bottom. This chronometer rating was done in 1835 of an American made chronometer, but you can see that, for example, the rates shown below are something like less than 20 seconds over a period of a month, which is very, very good. And so when you're trying to do a chronometer, you have to frankly understand the difference between accuracy and precision. One of my first jobs was as an analytical chemist, and they taught me at the time that I needed to make a distinction between accuracy and precision. Most people don't, but the thing about it is that accuracy says, how far do you deviate from a known standard? That's the measure of accuracy. Precision is how far do you deviate from the last reading? So if you're only something less than 20 seconds a day, then you can figure out accuracy by taking the last known accurate reading and calculating the number of days since that reading was taken, and thereby figure out the accurate time. So you have to have precision in order to get to accuracy. If your clock varies all over the map, you will never be able to figure out what the actual time is. So here's another chart, and this one is a temperature chart on a much more modern, this is from 1945, but it's a US Navy chart, and you see the 3 red circles there indicating the variation in time with different amounts of temperature. And you can see that it varies. This particular chronometer, which is a Nardin French chronometer, varies less than 1 second over about 40 degrees of temperature. And here's another example. I said French, I should have said Swiss, of course. Here's another example of checking a time over time, and you see that there's a variation in about 1 to 2 seconds over quite a considerable variation in temperature. So the other thing that ships did once chronometers were available to them is they often carried multiple chronometers. Here's a chart showing a ship that was carrying, would have carried 3 chronometers. And you have to think about the fact that you needed to have insurance against the chronometer being damaged, against the chronometer being stopped, either because of a defect or because somebody forgot to wind it. That is a very, very serious violation on board ship. If your job is to wind a chronometer and you fail to do so, you are in deep, deep trouble. So they would carry multiple chronometers and check them against each other to make sure that they were all more or less keeping time, and also as a way of avoiding damage and other kinds of distress. So how do you know local time? Well, the motion of the sun and the planets has been known precisely for centuries, just forever. Noon is defined as when the sun is highest in the sky, when shadows are shortest. Noon, oftentimes we say, well, noon the sun is directly overhead. Not really. It's when the sun is highest in the sky, because the sun is not directly overhead at noon every place on the globe. But when the sun is highest in the sky, that's when it's noon. So if you have a sextant and astronomical tables based on those calculations of the motion of the sun, you have created what amounts to an incredibly accurate sundial. And the math involved is actually quite simple. Just as I said, addition, subtraction, multiplication, division, and a good set of tables. So here's an example. If it is noon in Atlanta, which not quite, but if it is noon in Atlanta that you determine by using a sextant and astronomical tables, and say you know that it is 5:37 p.m. at Greenwich, which you have determined by looking at your chronometer, then you know that given the fact that there's 15 degrees of longitude per hour of time, Atlanta is at 84 degrees 0.4, and that is west of London. So the actual latitude would be minus 84.4. In those days, they used degrees, minutes, seconds to calculate things, but nowadays, most astronomers and navigators would use decimal degrees. So you know that it is minus 84.4. So this is how you could calculate longitude where you are. You use your sextant to tell you what time it is where you are, and you use your chronometer to tell you what time it is in London. And the math becomes really quite simple. So we now come to the coincidence. What was the coincidence that I mentioned? Well, in 1736, HMS Centurion, which was only 4 years old at the time, but it was 4 years before Commodore Anson took his trip, the Centurion actually carried H1, and it went on a test voyage to Lisbon. And it performed very well. In fact, it performed far better than the ship's navigator. And this was sort of a proof of concept, as they say in modern technology, that the idea of using a chronometer to determine longitude was a sensible idea. So this was the beginning of a technology that was to revolutionize navigation at sea. No longer did you have to do things like sail to a latitude and then go east or west and risk losing so many men to scurvy. And the chronometers then were made smaller, as we saw with H4, and they were made by the thousands so that every British ship of the line. And one of the things we think about is that this was before there really was any such thing as mass production. Mass production of precision instruments simply didn't exist at the time. So there's a whole bunch of machinations that went on with Harrison and the Longitude board, where they made him submit H4 to them and made him disassemble it in their presence so that they could see all the parts. And then he had to disclose his secrets to other clockmakers and so on, because the Longitude board was, they had to say, look here, we're going to have to make thousands of these things. So we have to know, first of all, that what you've done is mechanically feasible to make in the thousands, and that it can be done at a reasonable cost. So this was the beginning. And we know, of course, that Harrison fought and fought and fought to get his money, and finally did when he was very near the end of his life. But he did finally was justified in his belief. So there's another thing that you might find fun. I certainly did. There's a novel called The Golden Ocean by Patrick O'Brian. If you're a fan of seafaring tales, you may be familiar with Patrick O'Brian because he wrote a whole series of novels called the Master and Commander series. And lots of people have enjoyed these novels over the years. They are noted for being quite accurate in their details of seamanship and navigation. Well, this one came out in 1956. It came out before the Master and Commander series, but this is actually an account of the Anson voyage from Britain to the Pacific Ocean. And one of the things that I found so fascinating in this was that junior officers on board the ship, many of them signed up to be taught by a skilled navigator to calculate longitude. And this was because they could get an increase in their pay. They could actually get a higher pay grade on board ship if they knew how to calculate longitude. So the young guys would seek out an older mentor who could teach them how to calculate longitude. And the other thing about it is a great seafaring yarn, you know, with all the stuff you expect. And it also gives some account of what a great commander Commodore Anson was, how well revered by his men, and so on. So I offer thanks to two gentlemen from Chapter 160 in Boulder, Dave Cooper and Tim Schultz, who supplied me with documents, the rating charts and things like that that I used in this talk. And I am at the end, and I will be happy to answer any questions if I can.
Any questions?
And thank you.
Thank you. Thank you.
Yeah.
Tim, we thank you very much for joining us, and I felt give him a round of applause when you did.
You're very welcome. Thank you for having me.
I'd just like to make one comment, if I may. This finding the exact noon at your location by the highest elevation of the sun is a non-trivial process when you're on a rolling ship.
Oh, absolutely. Absolutely. There's all kinds of things, you know. One of the things that you got is you're looking through a sextant. And if you got a good sextant, you've got a gazillion filters and density filters so that you don't blind yourself doing this. You're also trying to stand on board a ship that is pitching and rolling with the waves and all that sort of thing. And Bill Tapp, famous watch repairer here in this area, who passed away this past year, but well known to many and all as being one of the finest watchmakers ever to have lived. He told me one time that he went out in his backyard and took a sextant and sighted the sun. And of course, knowing Greenwich was easy because there was radio and everything else. And but he was just standing on solid ground in his backyard trying to sight the sun. And he told me, he says, you know, he says, I did it several times. And the amazing thing was the house never moved more than a half mile, you know, so that's standing on terra firma. Imagine what it's like standing on board ship. Not an easy thing to do. A lot of skill involved.
George?
It was a good movie back early 2000s, based on Master and Commander.
Yes.
Yes. Yes. It was with that Australian fella. And yeah, Russell Crowe. The Golden Ocean is 1956, so it's earlier than the Master and Commander series, but it's the same guy. That is incidentally a pseudonym, Patrick O'Brien. It's his real name is something different, but they're great stories, rollicking yarns, and lots of authentic seamanship notations in them.
Well, Tim, we thank you very much for your time, your knowledge, and sharing this with us. And thank you.
All right. Thank you for having me.